Thank you very much for inviting me to attend this meeting. I wish I could attend in person, but also all your talks were during night time in California. So I hope I can look at the recordings, and thanks for all the recordings also. So I'm going to talk about a direct method for function approximation. There are some problems in machine learning which I have been wondering about ever since I started working on neural networks sometime in early 1990s. So first I will talk about what problems I was wondering about, and then an intermediate solution via diffusion geometry, and then I will point out what was still not finished, and then I will talk about a recent algorithm I found out for function approximation on an unknown manifold without knowing what that manifold is, and then I will show you some applications. And then if time permits, then because this is a meeting on PDE and uncertainty quantification, and fortunately or unfortunately, it was postponed by 2 years, then I had some time to work on this topic also. So if I have some time, then I will advertise some of the recent work in that direction, just to get more feedback. So to start with the introduction, as everybody knows in this audience, one fundamental problem of machine learning is we have a black box function and we want to approximate it based on some noisy samples of the function. And the methodology which is normally used and described in most textbooks is like this, that we have first to figure out what model to choose because we want to do, of course, some sort of optimization procedure to find the best possible model. But that requires that we prescribe in advance what kind of models we want to work with. And so people study the degree of approximation to the target function. And that gives an idea about what this VN should be. But the actual object of interest is not P star, but the minimizer of the actual generalization error. But that we cannot do because we don't know the distribution. So the only thing we can find out is the minimizer of this empirical risk. Okay, there are some shortcomings of this approach, which is lately becoming more and more clear. First of all, this means that I have to have a larger model complexity if I want a better approximation error. But if I'm going to do training with such a large model, then that becomes harder. So it creates a dichotomy between having a large amount of data and the training. Then normally we are defining a global error measure, loss functional, and that hides certain local effects in the function. So for example, if I take a simple example of univariate approximation of absolute value of x, then it has only one bad point on the whole interval, but that affects the error globally if you try to get a Fourier projection. And then recently it was discovered that if the initial choice of the weights in optimization is not done correctly, then the network becomes dead on arrival. And a couple of years ago, I observed that the whole paradigm of choosing the space V sub n based on degree of approximation can be quite misleading. So for the same class of function, when I did ReLU approximation, I could show that if you don't care about how the approximation was constructed, you can get a dimension independent bound. And so in particular, that would mean that the deep networks will not offer too much of an advantage over shallow networks. But if I insist on giving an algorithm for constructing such an approximation, then I have this curse of dimensionality very much. So, but it's all for the same class. It's not like the dimension independent bounds are for some class like Barron class, and dimension dependent bounds are for some other class like Sobolev class. They are both the bounds are on the same class. Both of them are unimprovable, but the only difference is whether it's a constructive proof or not constructive proof. So all this right from the beginning, then I was wondering, is this really all necessary? Can't we do something easier? So I have been wondering couldn't I possibly construct an approximation directly from the data? And without going through this generalization error, degree of approximation, and so on, just estimate the error between the model which I have constructed and the target function. The target function is not known, but I know that it belongs to some smoothness class. And ideally, the reconstruction error would be within a constant times the degree of approximation. And before I go further, again, I should emphasize that I'm not looking for a better degree of approximation because that can possibly be achieved just by using different ideas. And secondly, there are width theorems which say that, which give some lower bounds, and those bounds are quite often already achieved. So there is no hope of obtaining a better degree of approximation. That's not my intention. And I certainly don't want to claim that the methods which I'm going to describe are better than anybody else. First, I don't want to offend anybody. And secondly, another thing which is curious to me is when we prove theorems about approximation, we are proving them for classes of functions. But when we test them, then we are testing on one data set at a time. So there is no way that it can do better for every data set. And another thing which is still baffling me is the question of how to select features for the data. So classical machine learning requires that you deal with feature space to begin with. And I have no idea how to do this automatically. So there are some obstacles in this process. One is that we don't know where is the data. So it certainly does not become dense on a cube. Otherwise, we cannot avoid this curse of dimensionality, and it's really unreasonable to assume, for example, that the class of 1024 by 1024 images lies densely on a set of 1 million dimensions. And then the points y sub j's are not chosen judiciously as in classical approximation theory. They are just chosen randomly. And then there is noise in the values of the function also. That's also unavoidable in practical applications. So it's not so straightforward to do a direct construction, but still that's what makes the problem interesting. Okay, so one of the things I came across in around 15 years ago is the topic of diffusion geometry. And one part of the motivation is the curse of dimensionality. I think most of you already know this. So if you have a matrix space X and a compact subset, and you take some parameters on the function and then want to reconstruct the function somehow, then what is the best error that can be done with whatever clever parameter selection and whatever clever reconstruction algorithm anybody can devise? And that's the nonlinear n bit defined by Howard, Micheli, and DeVore. And it's well known that for approximation of R times continuously differentiable functions on a cube of dimension q, the width has to be at least m to the minus r over q with m samples. So there is a curse of dimensionality here indicated by this q in the denominator. Okay, how can we solve this? This is a theorem. We cannot overcome that. What we can do is to just imagine that the curse is not there. That's a very simple solution. So the manifold assumption says that my data is actually sampled from a compact, connected, orientable, smooth, unknown manifold with respect to its volume measure. And this unknown manifold is a small dimensional submanifold of a high dimensional ambient space. So that amounts to practically assuming that the curse of dimensionality doesn't exist really for my problem. Then the main problem though is that this manifold is unknown. I don't know if you can see my cursor or not. Can you?
See it.
You can, okay. So because the manifold is unknown, then some of the questions is to figure out what that manifold is. And then we can do function approximation. So there is a old theorem, very classical by now, by Belkin and Yogi, which say that if you have the Laplace-Beltrami operator on the manifold, then uniformly for x in this manifold, there is an approximation of f of x given by this integral expression. And it actually approximates this actual manifold Laplacian. Okay, there is, from my point of view, it indicates a little bit of a saturation. So if you think of just this integral expression like the solution of a heat equation, then it is supposed to approximate f of x, but it cannot do so at a rate lower than little o of t. If it does, then this theorem says that the Laplacian of that function will be 0. So that was one thing which was bothering me for some time, but let's worry about it later. Here is the general approach to the problem. We construct a discretization of that integral, which is called the graph Laplacian. And Beltrami, Yogi, and Lafan, and Amit Singer, and so on showed that this graph Laplacian actually approximates the actual Laplacian on the manifold. And then we have to find the eigen-decomposition of this, which is approximated by the eigen-decomposition of the graph Laplacian. And then we have to construct the approximation using this eigen-decomposition. And then recently there are some efforts by Schmidt, Heber, and some others where they tried to find instead the atlas on the manifold. But of course, that all that has to be done approximately because we don't know what the manifold is. And everything has to be done from the data. Okay, so because it is my hour of glory, I will advertise my work, but in the direction of function approximation. But of course, there are many other people who have worked on this problem. So the setup here is that we have an IID sample from the volume element of the smooth, compact, etc. manifold X, which is unknown. In theory, we assume that there is a system of eigenfunctions of some PDE with eigenvalues lambda sub k. And they are, in practice, they are computed approximately by the graph Laplacian. Then I consider the span of the initial phi sub k's as my approximation space, the model space. And then I want to consider my approximation in the sup norm. In the sup norm, classical approximation theory results tell me that one nice way to define smoothness is by figuring out how fast does the distance of f from pi sub n measured in the sup norm decreases to 0. So in that sense, the gamma will define the smoothness of it. The nice thing about this is I don't need any structure on the manifold. It's just entirely dependent on the space of approximations. And one of the essential ingredients here is the quadrature formulas and if kernel. The kernel is defined by such a low-pass construction. It turns out to be highly localized, which is an important property in this theory. And then the other ingredient is that if these y sub j's are actually sufficiently dense on my manifold, as assumed by the theorems of Belkin, Yogi, Lafan, and so on, then there exists such quadrature weights so that for every p in my space of approximants, this quadrature formula is exact. The WJs don't have to be positive, but they have to satisfy this inequality, which is called Marcinkiewicz-Zygmunt inequality. In the lowest constant C, which works here, I will denote by some norm expression for this measure. So any system like this which satisfies Marcinkiewicz-Zygmunt inequality and quadrature will be referred to as Marcinkiewicz-Zygmunt quadrature measure. The one thing to note though, this has nothing to do with the value of the function. It has only to do with the values of these y sub j's. So this situation is reasonable if we have a lot of functions to approximate on the same manifold, on the same data. Okay, but after that, then the construction is very simple. There is no more optimization, nothing like that. We just take our samples yj, zj, and plug them in the localized kernel in such a way using these quadrature formulas defined only based on the y sub j's, not the z sub j's. And then this approximation does the right job. So with high probability and the right number of samples, we have the right rate of approximation here.
There's a question here. I was wondering about the notation. Is Zj the output observation?
Yeah.
And yj the input observation of your function? Okay.
Yeah. and it takes into account the noise. So Z sub j is the actual value plus the noise epsilon j.
Thank you.
Okay. So I have this theorem which is known to be the optimal theorem. And this doesn't include any of that rigmarole about generalization error and best approximation and empirical risk minimization and or anything like that. Whatever optimization is required is done in solving a system of equations involved in this Marcinkiewicz-Zygmunt quadrature. But that's a system of linear equations, so that's a much easier problem to deal with. So then I thought I'm done. So now I have completely revolutionized machine learning, and I was quite happy, and I started giving talks on them. And then Lorenzo pointed out to me that no, that's not enough. So that's then became my mood. So the reason why it is not enough is that one needs the prior knowledge of all the test data for the construction of the graph Laplacian. So it is essentially a semi-supervised learning method. We don't get a model at the end. And then we don't really know the system of eigenfunctions and eigenvalues. All we know is the approximation to those via graph Laplacian. The graph Laplacian itself is very sensitive to the choice of some parameters in the construction. And so all these errors which go into the construction and the solution of the eigensystem problem, it might destroy the approximation error. So then the question is, can we approximate this F directly without doing this eigen-decomposition or without trying to approximate an atlas or any such two-step procedure? I would like to have a one-shot procedure. Give me the data and I give you the approximation. So I was able to find such a one-shot method last year, and it depends upon Hermite functions. They are polynomials multiplied by e to the minus t squared over 2. And these are the orthonormalized Hermite polynomials. They are based, classically they are defined via a Rodriguez formula, but I find it more convenient to define them recursively in this way. So then it's easy to write a code to compute this. And then I need certain parameters defined by this power series expansion. Okay. Remember that my dimension of the manifold is little q, and then I will have an ambient manifold which is of dimension capital Q. So I will use this with different values of d. So then I construct this univariate kernel. In classical approximation theory, if you look at the book of Hardy on divergent series, this is called an Norlund mean, but I could not find references to properties of such Norlund means. Doesn't matter, but after that I construct the same filter as before, except that there is a technical kink of having square root of m here. But of course that doesn't matter. We just define another function h if you want to have m here. The only thing where it matters is that now we are going to get polynomials of degree n square when I denote the index n. And once more, the filter looks like this. It's 1 in a vicinity of 0 and 0 outside of 1. So here is the theorem. I have a smooth compact Riemannian manifold. Mu star is the volume measure. These are noisy samples. This time my thinking is like this, that we have noisy samples, but it's common in numerical analysis that instead of saying that there is an error in the value of the function, we say that the function is accurate, but it's evaluated at a wrong point. So that wrong point will be y epsilon. The value of the function at y epsilon will be fy epsilon. And then the expected value corresponding to y is f of y. So in particular, I need to know at what y is this function supposed to be evaluated. And then I'm assuming that the marginal distribution of this y is absolutely continuous with respect to the volume measure, and it has this form f sub 0. And then I define my approximation using a parameter alpha in this way. Once more, it's a straightforward approximation. This time I don't even need quadrature formulas. These are the function values which are given. These are the input values. This is the univariate kernel which I have defined before. And this is the Euclidean norm in the ambient space. So the manifold doesn't enter anywhere into the picture except through this dimension little q. And I don't need to assume anything about the target function or the nature of the noise or anything like that in order to define this approximation. Okay, then of course I need a smoothness class if I want to define degree of approximation. So this is a little bit complicated to define in this case, but I hope that will serve as a good advertisement of my paper. So in particular, if gamma is an integer, and then this class contains all the gamma times continuously differentiable functions. If gamma is 1, then this contains the class of all Lipschitz continuous functions on X. And now here is the theorem. So under this, if I choose my parameter alpha in this way, and the number of samples satisfy this condition, which means I have to choose n so that this inequality is satisfied. Then with high probability, we have such a bound with n to the alpha gamma. Here there is no restriction on gamma, but effectively you see that the rate will be like 4 at the most. So in particular, if I choose my f to be 1, then I get a density estimation. And the interesting thing here is that this kernel is not positive. So it's not a classical probability density estimation. But if you insist that it has to be positive, then don't put a positive kernel here. It's known in approximation theory that if you have a positive kernel here, you cannot get a good rate of approximation on this side. What one can do is to take an absolute value around the summation. Okay, then if I sample my data.
Another question.
Sorry, yeah.
Another question. Shouldn't the rate depend upon the manifold dimension? Maybe it does. If you can remind us what the alpha and the gamma are.
It does via this little q. So
but the rate, the accuracy.
Sure. So the number of samples is n to the power q times so on. So yes. The n is dependent on m via this. Okay. So of course, it depends upon little q, but it does not depend upon the ambient space dimension, though.
Yes.
Yeah. And then if my samples are taken from the volume element as it is customary in diffusion geometry, then I get this rate of approximation, again with high probability. And of course, to get the rate of approximation, I need to have assumptions on f and f0. But for the construction of this estimator, I don't need any assumptions. It's truly a universal approximation. Okay, so when I present such theorems, then I'm never sure if it is going to work in practice or not. Everything looks dandy in theory, but then I feel diffident about applications. So I was lucky to have a couple of young people who put this in practice. And oh, I don't see the time now. Okay. So one of the applications was in blood sugar prediction. When you have such continuous glucose monitoring devices, if you have advanced state of diabetes, then they put it under your skin, and then it measures the blood sugar every 5 minutes. And then the problem is to figure out what is going to be the future blood glucose level, not just the level, but also the direction in which it is going up or down. And then the numerical errors are not that important here. It doesn't matter very much whether my blood sugar is 126 or 126.1. What is important is, am I in danger or not? And so some endocrinologists came together and formulated a gold standard called PDEs. So depending upon whether the diabetes is high or low or normal, and depending upon how accurate this blood glucose level is there and the direction is right or wrong, then we have 3 kinds of error. Accurate means everything is okay. Benign means everything is not okay, but it's not dangerous. And error means it could be dangerous. And then the important problem is to make an accurate prediction 30 minutes ahead of life. If in 30 minutes we expect that some smart device can inform a nurse or so, and then she can call and tell the patient to drive immediately to emergency or otherwise take some remedial actions. So using these techniques directly, our method gave these readings for low blood sugar regime and normal blood sugar regime and high blood sugar regime. And the important thing to know, to focus on is the error. In the normal blood sugar readings, we did not do too well compared to another method called FARL. But in the other regimes, we made even the deep learning toolbox of MATLAB, and considerably at that. Okay. So, and also this is based on a clinical data, not simulated data. So the other application was in hand gesture recognition based on macro Doppler radar readings. So somebody took a macro Doppler radar and observed the signatures of the radar readings, and they are taken over different times for different hand gestures like this. And you see that sometimes the signatures are about the same, like for these two gestures, the signatures are very similar to each other. So it is a slightly difficult problem. Then I was lucky to find an undergraduate student called Adam Kuo, who did a senior project with me, and somebody called Eric Mason, who used to work for the Naval Research Lab, who gave us this data. And they tried our technique. Of course, they had to do quite a bit of pre-processing, sometimes like a PCA processing or SVD or something like that. And then they had to do some thresholding. So there was, it turned out that the thresholding together with the PCA gives us the best results, and my method. So the binary means the kind of thresholding they were doing, whether they just tested whether something is above 1 or not. And PCA denotes that they did PCA. The log SVM means that they treated my kernel with degree 16 or degree 64. And instead of using my formula directly, they are going to train a support vector machine. Okay, and these are the results then. Our method does slightly worse with this normalization compared to k nearest neighbors, but it does substantially outperform the both the deep networks which are used in practice in this discipline. And of course, the training time here is substantially smaller than the deep network. Okay, if you use another normal, another kind of thresholding, which is called N normalization, then we outperform also with 64 degrees every other algorithm known to us, and with a small training time. I should note here that this is a very new method, so it is possibly to evaluate this in a fast and efficient manner. But I was nervous about whether or not it will work in the first place, let alone training time and test time and evaluation and such. But now it has to be kept in mind that these deep networks were trained using the most sophisticated software, and this is a relatively unsophisticated undergraduate way of doing things. But nevertheless, it's I like this fact that it worked better than deep networks, in fact, in spite of being so simple. Okay, then because this is a conference on PDEs and uncertainty quantifications, and because it was there is always a silver lining to some bad events. So the pandemic allowed me to do nothing else but do some work, and so I was able to do something about PDEs and uncertainty quantification. So I guess I still have some time. Here is the motivation. So we have a partial differential equation, and we want to treat it like a mapping from the boundary, the initial condition to the solution, subject to these periodicity conditions. So of course, numerical analysis has many techniques for this, but they are normally doing one differential equation at a time. Here the idea is that we consider the whole class of initial conditions and the boundary conditions, and no, I'm sorry, these are initial conditions, and then treat this as a mapping from the initial condition to the solution. So We don't have to actually solve the PDE. We work with the training data. And then the uncertainty quantification I learned from many lectures. Here is a typical problem there. We have a random function a omega x, and out of this we are not so interested in the solution, but we are interested in some quantity of interest in the solution. It could well be the value of the solution at x, but in the literature I found that they are interested in the expected value or the variance of this u. From my point of view, in an abstract sense, here is a family of functions a, and then I'm trying to approximate this operator taking a to this quantity of interest, whatever it is. And there is a well-known paper by one of the organizers of this meeting, together with Cohen and Dibor. So in the abstract sense, I consider two matrix spaces, and then a compact subset of one of the matrix spaces, and I have an operator taking arguments from this compact subset of the matrix space and values into another matrix space. And I assume that this is at least a Lipschitz continuous function. And then the problem is we are given finite amount of information about the f, like finitely many values of these functions denoted by a, and finitely many values corresponding to the solution u. And then I want to find an efficient method to approximate this function. Not solve any particular differential equation, but we have already solved a bunch of differential equations with different data points. And I want to use that information to solve every other differential equation. And then, of course, I want to estimate the degree of approximation. So here is a general reduction of the problem. We have a mapping from the matrix space to another matrix space. And of course, if I restrict it to continuous compact subset, then I will get a compact subset in the image. So I can have an information operator analogous to the theory of widths, and then a reconstruction operator like this. And then hopefully somebody has chosen these things so that the distance between f and this reconstruction measured in the metric of x is less than the width. And the same sort of assumption at the other end on the y space. So I'm not so concerned about how to choose the IDX and ADX and I and A operators. That depends upon the application in question, but I assume that it is known. Typically, the I operator will be the values of the function, or maybe the Fourier coefficients of the function in some series. The reconstruction algorithm will be similar to what I just described to you. And so then the problem is reduces to approximating a function from a Euclidean space of d variables, the amount of information on the input function, to another Euclidean space, which is the amount of information on the target function. And then this is the goal here. So this reduces the problem to something which we know how to do. The difficulty is that both the d and m will have to be very large. So pictorially, this is the setting. We have an input function, we have an parameter taking procedure out of this. All that is pre-processing, out comes a vector. I find it convenient to map it from the Euclidean space to the sphere of the same dimension by using a trick used in a paper of Francis Bach. And then I want to use some approximation procedures here for every component in the information of the value of this functional. And then it produces an approximation to the components f1, f2, fm. If I feed it to the reconstruction procedure at the other end, then I should get the value of this functional. A priori, it looks like I'm going to need a complexity d times n times m, but my construction will allow me to construct these boxes using the same parameters. So in reality, the order will be d plus m times m. Sorry, d plus n times m. So it's a fairly, it's a substantial improvement on the complexity. Okay, how can I do this? Again, the problem is that the D is large, the M is large, and the complexity of the approximation, they all need to be large in order to get good results. And that actually there is this curse of dimensionality running around everywhere, and so we need to do a very careful bookkeeping of all the dimensions involved. That's what took so many months of efforts. Every time I did this calculation, I got a different result. And then I did it again after a month or so, and then I got again a different result. And then when I got the same result 2 times in a row, then I thought, okay, now I'm done. Then I wrote it down and read it again and again to make sure it was all right. So I'm going to assume some extra smoothness of it, and how to define the smoothness is already a question in its own right. And I have to keep track of the dependence on the dimension. Then the other remedy was so that I use only, if I want to approximate f at capital F, then I'm going to take values only in a small neighborhood of f. So it amounts to distributed learning. I divide this set k of x into small balls, and then I will deal with each ball separately. And then my approximation should adjust automatically to the local smoothness. I don't have to know in advance what the local smoothness of these information operators is. So here is the conversion of the sphere, which is also in the paper by Francis Bach, also in my own paper with Tommaso Poggio. So here is the definition of the sphere. I have a Euclidean space here in which the information operator lives. I will just project it to the center of the sphere, which gives rise to this coordinate chart. And now I can approximate on, focus on approximating a function on the sphere to the real line. Okay, now I'm very much in a familiar terrain, except for keeping track of the dimensions. So here are some ingredients in the construction. I will need to know about Jacobi and spherical polynomials, of course. Then I need to define the smoothness in the right way. Then I need the quadrature formula as before. And of course, I will need the right kernels. So here is some notation. This is again the volume measure on a sphere of dimension d. The d will be different in the domain space and the codomain space. The omega d is the volume. Pi is the set of all spherical polynomials. The Jacobi polynomials are orthogonal polynomials with respect to this weight function on the interval. And I define a certain univariate polynomial like this. It has the property that it is the reproducing kernel for this space. So if I integrate a polynomial against this kernel on the sphere, then I get back the value of the polynomial. It is technical, but it is standard. Then the smoothness class is something which also I had to struggle with for some time. So of course, the classical Lipschitz condition says this, which I can reformulate it in this way. And then I can say that, okay, I can think of this. If I fix an x, then I can think of f of x as a constant function. And so this condition I can reformulate by saying that if I look at all polynomials of degree 0 and look at this difference, then the minimum is less than infinity. That's a reformulation of the Lipschitz condition. And now the choice was simple. I just replace this by a higher exponent and this by a higher degree. And so the smoothness, local smoothness of a function at x is defined in this way. Locally in a small neighborhood of x, the degree of approximation of f by polynomials of degree r should satisfy this condition. And then this is my local smoothness class. If it happens at every x for the same r, then it is the global smoothness class. Okay. Then the next ingredient is the quadrature formula. The theorem which I showed you before works here, except that the constants are dependent in an unspecified way on the dimension of the sphere. So that is still an open problem. But luckily there is a quadrature formula which works, and it is only an existence theorem. But it is also fairly well known. There are always, if you have any kind of finite dimensional space, then which contains 1, then there are positive numbers and points, so that such an exact quadrature formula will hold for every polynomial in the finite dimensional space. And then I'm going to denote this by this fact, this MZQ means it's a Marcinkiewicz-Zygmunt quadrature. The D means we are talking about sphere of dimension D, and N means this holds for all polynomials of degree 2 times n. Okay, then we need a kernel, and this also took a tremendous amount of effort and trial and error to figure out what to use. And here is again the reproducing kernel, and here is a special Jacobi polynomial with special parameters which are normalized to be 1 at 1, and then I multiply this by this exponentially decaying factor. So that's my kernel, and corresponding to this quadrature formula, then I have this. I have written this in an integral format, but please remember that this is a quadrature formula, so this is actually a finite sum, having exactly the same number of points as the dimension of the space if I use the Chekhov quadrature formula. The Chekhov theorem is an existence theorem. If you want to use this in practice, then presumably you want to do some solution of equations in the right way. But it all depends only on the locations at which the f is sampled, not if it's just like before. So all this is a pre-computation, which I showed you pictorially before. And then this construction again is a universal approximation. I don't need to assume any prior on f, other than the fact that it is a continuous function. Okay, so then the degree of approximation is defined like this. This just states that this is a near-based approximation. This is the constant which appears in the Marcinkiewicz-Zygmunt inequality. If you use the positive measure, then this constant is just 1. But the interesting thing is here is a tractable constant that this does not. You know now the exact dependence on the dimension, and it is not too bad. It's just dimension to the power 1/6. Okay, so this is a near-based approximation. And here is the degree of approximation theorem. So let's say that my function is smooth locally at x according to the smoothness R, which can also depend upon x. And my n and the dimension satisfy such a technicality. I choose a small ball of radius n, and then I get this degree of approximation. Remember that if nu is a positive measure, then this constant is 1. This is the normalization which enters into the definition of local smoothness, and this is the exact rate which is expected. The novelty is that this constant is a small constant depending upon the dimension. Okay, this operator is defined globally as an integral over SD, or likewise the sum over all the quadrature nodes on all over the sphere. But you can do this also by taking only the values of x, the values of y in a small neighborhood of x, and the neighborhood is prescribed by this. This delta was the radius of the ball for which the function has this smoothness. Okay, so that's theory. If you have random samples, then one can discretize this using concentration inequalities and such, and we get the same sort of bounds. Okay, so thank you very much.